Okay, so everything that we've been doing so far leads us to the broader topic called gas laws. Now we're entering a point where those of you who are doing or have done chemistry are going to have an advantage, because this crosses over with a lot of what you will have already done in chemistry. So, yay! If not, don't panic. I will tell you everything you need to know. I think a lot of you are doing chemistry though, so you should be fine. Okay, so first thing we need to talk about is something called the kinetic theory of gases. Now this is a really fundamental theory, and we're going to talk about it a lot. Now, it's not a perfect theory, kind of like a lot of the things we talk about. It works for some things, but not all, and that's because it's based on a lot of assumptions. So you are going to have to learn those assumptions because they can ask you for them. You can also use them to explain why any estimates you use from these calculations that we will look at will only be estimates, and it's because of all these assumptions it's based on. But boiled down to its basics, the kinetic theory of gases says that any gas consists of point molecules moving about with random motion. So this links back to the Brownian motion we were talking about last time. That's the random motion that we saw. We just built on it a little bit, and we're now saying that we're going to treat all the molecules in the gas as point molecules, so meaning that they don't really have any volume, they just act at a single point, and that all of them are moving in a completely random way. So already you can see in this theory we are making a lot of assumptions. But we are going to use this theory to explain pressure that's caused by gases. Just check, we do remember what pressure is, don't we? See, I'm waiting because I know there's a deafening silence where you'll go, I think I remember how to calculate it. So I'll just remind you real fast that pressure is force divided by area, where force is newtons, area is meters squared. Pressure is measured in pascals. That is the SI unit, pascals. So 1 pascal is 1 newton per meter squared, and standard atmospheric pressure is 101 kilopascals, just to give you an idea. We do not, I repeat, we do not use atmospheres as a unit. You may have somewhere floating around in your head that room pressure is 1 atmosphere. We are never going to use that unit. It's not an SI unit. If you want to talk about atmospheric pressure, it's 101 kilopascals. You know, like 101 Dalmatians. You're not expected to know that, don't worry. It's just a number I'm telling you. So, we are used to this idea, though, that there is an amount of pressure due to the pressure of the atmosphere. So that must be being caused by the fact that there are gases in the atmosphere. So what we need to think about is, how does a gas exert pressure? Well, a gas is made up of molecules, and those molecules are in constant random motion. When one of those molecules hits a surface, it undergoes a momentum change. Now, hopefully you remember about momentum from last year, so an object's mass times its velocity. And if it hits a surface, it's going to rebound. Now, we're going to assume that those are perfectly elastic collisions. So it goes from having a momentum of mv to having a momentum of minus mv, because its direction has changed completely. So bouncing off the surface, just in case you couldn't imagine it, there's a little picture for you. So if we think about Newton's second and third laws, that means that the surface must be experiencing a force, because we're seeing a change in momentum, so there must be a force causing that change in momentum, and that force has got to be equal to the mass times the acceleration that that object is experiencing, and because I've got two bodies involved, they're going to experience the same force. So basically the pressure exerted by the gas is equal to the total force from each of those collisions by the molecules on a unit area of the surface. So basically gas pressure is caused by the change in momentum of gas molecules when they hit the surface of a container, or they hit a surface of whatever. So if we're talking about, you know, the pressure that we feel, it's the pressure of the molecules bouncing off us. Okay? and as we said before, the pressure is just the force over the area. Now I said there are assumptions, so let's just pop through them. I've already said this one, that the molecules are points, so the volume is so insignificant compared to the volume of the ideal gas that we ignore it. We also assume that the molecules don't attract each other, so that there are no interactions between the molecules of the gas. We assume that the molecules move in constant random motion. We assume that all collisions between the gas and the container are elastic. We assume, nearly there, I'll stop erring, I promise, that the time taken for a collision is much shorter than the time between collisions. So basically the collisions happen so quickly that we don't need to worry about the fact that they take an amount of time. Finally, we assume that any sample of the gas contains a large number of molecules. So we are assuming that there are huge numbers of these molecules, so it's not like there's only one or two. There's enough that we don't have to worry about how many collisions per second, because there's a huge area but not many molecules. We assume enough that we don't have to worry about that. So, once we have this theory that we've said, right, okay, it's got lots of problems with it, but based on the fact that we're saying that the pressure we're feeling is due to the collisions of these molecules, what we can then do is think about how pressure is going to be affected by changes of certain circumstances. So for instance, the temperature. So let's just think, what's going to happen if I increase the temperature and why? That's your thinking time. So, if we increase the temperature of the container, what we'll find is that the molecules are going to move faster. So that means that more molecules are going to hit the sides of the container every second. And when they do, they're going to be moving faster. So the size of my change in momentum will be bigger. So that means that the force being exerted will be larger from each molecule. So the overall force will be larger. If the overall force is larger, the pressure will increase. So if I increase the temperature of a gas, the pressure will increase, and that's why. So let's think about the volume then. What happens if I change the volume of the container? So let's say I decrease it. So if I decrease the volume of the container, that will increase the number of collisions per second, because the molecules don't have to travel as far to go from one side of the container to the other, but they're going at the same speed, so that means there will be more collisions per second. If there are more collisions, that means that there will be a greater force being experienced by that surface. So the pressure will increase. Okay? We are going to have a look in a lot more detail as this topic unfolds at how this kinetic theory can be quantified. So we will look at this in a very quantifiable manner. For the moment, you need to understand it qualitatively. You need to get those steps in your head, because this could be the kind of thing they might ask a longer answer question on. Now, here's the bit where the chemists have the leg up. Whilst we're doing this, we are going to be looking at gases and we're going to be looking at molecules. And we're going to say, well, I've got this much gas, and we need to have an idea of how many molecules there are. So that means we're going to be using this wonderful thing, Avogadro's constant. Now, you may or may not remember Avogadro's constant if you haven't done chemistry, but it is just a number. And its proper definition is that Avogadro's constant is equal to the number of atoms in 12 grams of carbon-12, which is 6.02 times 10 to the 23. Now, note it has no unit, because it's just a number of molecules. Now, the other way to remember this is that Avogadro's constant is just the number of molecules in 1 mole, or that 1 mole is this number of molecules. If you can remember it that way, you can always work your way through from a mass to a number of moles and vice versa, or a number of molecules. So just try and remember that. So we're going to be talking about the amount of substance a lot. So the amount of substance is the number of moles. It's one of those SI base units. You may remember those from early on back last year. We looked at base units, the 5 units that everything can be boiled down to. And moles is one of them. So amount of substance is just the substance measured in moles. And 1 mole is Avogadro's number of particles. Now, the number of molecules, the capital N, contained in N molecules, N moles of a substance, sorry, will always be given by N, big N, the number of molecules equals the number of moles times Avogadro's number. So, how many molecules I have is equal to how many moles times how many molecules is in each of those moles. So it should hopefully be pretty straightforward to get between those two. If you just remember that 1 mole is Avogadro's number of molecules. So molar mass is the other thing that you are going to see. Molar mass is just equal to the mass of 1 mole of a substance. So, knowing that, if I want to know how many moles of a substance I've got, that is going to be equal to the mass of the substance I have divided by its molar mass. And that will give me the number of moles. Now, sometimes you have to go the other way. You will often be given the number of moles and the molar mass, in which case you just do molar mass multiplied by the number of moles gives you the mass of the substance that you have. If you just think about what each of those terms mean, you should very easily be able to work your way through it. People sometimes get confused because, I don't know, they see these words and they panic. Just think about what all the terms mean and you'll be absolutely fine. So, I mean, the key example is that, so for molar masses, is that if I've got a mole of carbon 12, that's 12 grams. If I've got a mole of O2 molecules made of oxygen 16, that would be 32 grams, because I've got 2 lots of each oxygen would be 16, so actually 32 grams. A mole of carbon dioxide molecules is 44 grams. You're never going to have to work these out, you're just going to need to, you'll be told them and have to use them to find either a number of moles or the mass of a substance. So I will do a lot of practice on these ones. Hopefully, chemists, you don't even need these last few slides and just whiz through them. Non-chemists, just think about what the terms mean. If you get the definitions down, then you can just think your way through how to find your way. But we will practice these, don't worry. Okay, as I said, if you have any questions, don't forget to ask me. I wait for the day that one of you asks me a question. I will probably die of shock. But until I see you next, don't do anything stupid. That's all. I've got to think of a sign off for these, haven't I? Okay, anyway, so I'll see you in class.